Good morning, everybody. It's Tuesday, April 7th. I want to thank you guys for getting your assignments in. Make sure that keeps up. You guys doing a great job asking questions. I very much appreciate that. So that'll hopefully continue today. My anticipation is that today will be a relatively simple concept because we're really just essentially putting everything together from the last basically week. Okay, so it should be easy. The only thing we could potentially run into is the same thing that we run into pretty frequently, which is sometimes we get hung up on finding a specific derivative, but the concept I think you guys will have no problem with, okay? So we're still on section 3.3. Don't freak out by the part where it says graphing. Also, before I forget to mention it, you're going to have to ignore the directions or part of the directions today for the assignment because it says use a graphing utility, use a graphing calculator to find all critical points or all relative extrema, whatever the case may be. We're going to do that, but basically what we're going to look at today is we're going to look at what doing the first and second derivative tests allow us to do in terms of graphing. They allow us to know a lot about the nature of a graph without actually going ahead and graphing it, okay? So we're going to look at this one as kind of our sole example. If you'll notice this one right away, you probably recognize that it's a fraction. But here's the good thing about this one. The fact that the numerator of this fraction is just a 6, it's just a constant, means that we don't actually have to differentiate using the quotient rule. That was a big hang up yesterday for us. That's why I sent out number 5. Even after my clarification video, I still had people saying I'm still having a hard time differentiating number 5, and it was because it was a quotient rule problem. This one doesn't have to be. You can turn this into a chain rule, right? You can move this x squared plus 3 up with the 6 and then just give it a negative exponent. And again, the reason we can do that is because there's no x in the numerator, okay? We can just kind of make it relatively simple for us there. Okay, so here's what we're going to do. We're going to find the first derivative, and then we're going to talk about what that does for us. Okay, so differentiating this one time, you bring the negative 1 down, multiply it by the 6, so we get negative 6, x squared plus 3, drop the exponent down by 1 to a negative 2, and then multiply it by the derivative of the inside, which is 2x. Okay, if we clean this up then, if I clean this up, I'm just going to write it as a fraction. The negative 6 and the 2x stay on top, so negative 12x. The x squared plus 3 goes to the bottom where it becomes 2. Now, the reason I did that, okay, the reason I did that, even though I'm going to potentially move it back up when I go to differentiate again to find the second derivative, is today we're going to do both. We're going to pause when we get our first derivative, and we're going to find the critical numbers for it, okay? So the critical numbers for this derivative, if you think about it, the denominator is kind of weird because we're always like, okay, it's a fraction. The critical numbers are whatever numbers make the denominator 0. But if you think about it, the only numbers that would make the denominator 0 are imaginaries because x squared plus 3 can't be 0. Okay, when you square a number, you automatically guarantee it's a positive number or 0, and then you add 3 to it, you're guaranteeing that it's a positive number. So there is no way to make the denominator 0, which means the only critical number is 0 itself, because if you plug 0 in, that makes the top 0. Negative 12 times 0 is 0. So here's what we have. At 0, okay, so x equals 0 is a critical number for the first derivative test. So plug it back into the original function, see what you get. You get 0 back into my original function, gives me 6 over 3 or 2. 0, 2 is a maximum or minimum. Remember, the first derivative test tells us maximums or minimums, not points of inflection. We're going to leave that there, and we're not necessarily going to worry about finding right out of the gate which one it is, because we should be able to splice this point with what we find in the second derivative to determine what exactly we're working with here. And if not, we can just plug points in. All I would have to do is plug in something to the left of 0 and something to the right of 0 and see if my y values were above it or below it to determine if it's a max or min. We might have to do that, but we'll come back to that. Okay, down here now. I'm going to move this back there. So I'm going to move this, and again, I'm going to just, well, We could or we don't have to. Essentially, now there's an x in the numerator, so now I guess what we could do to find our second derivative is instead of moving this whole thing back up and then using the product rule and the chain rule, we could just do the quotient rule, right? We could do our quotient rule here, and it'll maybe help us see things a little bit better so we don't get hung up when we see it today. So let's do it. Let's do quotient rule to find our second derivative. Bottom, x squared plus 3 squared times derivative of the top, which is negative 12, minus the derivative of the bottom. Derivative of the bottom is going to be a chain rule derivative. So 2 times x squared plus 3, now to the first power, times that by the derivative of the inside, which again is 2x. But now we got to remember that's the derivative of the bottom times the whole top, negative 12x. Okay? All over the bottom's squared. So x squared plus 3 now instead of being squared is to the fourth. This is very similar to the one we got hung up on yesterday, so I think this was a good thing to do. Let's factor out x squared plus 3 from both sides of this difference, okay? So from both sides of this subtraction problem. So when we factor that out, x squared plus 3 on the outside, what are we left with in both of these terms? Okay, so when I'm left with here, when I take 1x squared plus 3 out, I'm still left with another x squared plus 3. So now why don't I just go ahead and distribute negative 12 to it? Negative 12x squared, negative 12 times 3 is negative 36. Okay? Over here, when I take that x squared plus 3 out, I'm literally left with, here's that minus sign, 2 times 2x is 4x, times negative 12 is negative 48x squared. Okay, so I'm not even going to, well actually I am, sorry I lied. I am going to bring my whole denominator down because I'm going to be able to cancel part of it off. It's x squared plus 3 to the fourth, and there's an x squared plus 3 to the first. This x squared plus 3 can cancel one of those off, so now there's only going to be 3 of them on the bottom, and my second derivative is one step away from being found. All I got to do is combine like terms up here. Negative 12x squared, double negatives here go to positives, plus 48x squared gives me 36x squared. Bring down this minus 36 all over x squared plus 3 to the third power. There's my second derivative that I can now find critical numbers for. All right, figure out when it's going to be 0 or undefined. And those critical numbers will give me points of inflection. This is what you were working on Friday and yesterday, okay? There's still no way to make the denominator 0. It's still x squared plus 3, which by its very nature cannot be made negative, okay? So the only critical numbers we're going to get here are the numbers that are going to make the top, 36x squared minus 36 equals 0. So if I add 36 and then divide by 36, I'm going to get x squared equals 1. The square root of 1 is positive or negative 1. So, positive and negative 1 are both points of inflection. So, at negative 1, I got to find its y coordinate, and at positive 1, I got to find its y coordinate. Negative 1 all the way back up here into my original function is going to give me negative 1 squared is positive 1 plus 3 is 4, so it's 6 over 4, which is 1.5. So at negative 1, 1.5, we have a point of inflection, okay? Then if I plug in positive 1, I'm going to get the exact same thing. Positive 1 back up here is 1 squared is 1, plus 3 is 4, 6 divided by 4 is 1.5. Those are my points of inflection. So, points of inflection. This is going to be exactly what you're doing on your assignment today. You do your second derivative test to find any and all points of inflection. The last thing that's left to kind of answer here is, was this point a maximum or minimum? Well, this is where the graphing nature comes into play. If we just kind of eyeball this or just sort of generally sketch it, if you just put these points on here, these are points on the graph, negative 1, 1.5, so that's left 1, up 1.5. That's a point where the curvature changes. Positive 1, 1.5, over 1, up 1.5. That's a point where curvature changes. And then all you think about this, 0, 2 is a point on here. So if we look at this, we can realize that if those are 2 points on the graph right here and they're points of inflection, what must be happening here is this. 0, 2 must have been a relative or potentially an absolute, but it was a maximum because it's above those 2 points. So in all likelihood, here's what we have. We probably have a concave down graph on both sides of 0, 2. So it's concave down there, it's a frowny face. And then what in all likelihood happens is this. It changes course forever into a smiley face and into a smiley face again. So remember, these are points of inflection. They're points where the concavity changes. So it goes from being a smiley face to a frowny face pretty abruptly. And then same thing over here. It goes from being a frowny face to a smiley face. Okay, concave up versus concave down. And then the first derivative test, all we have to do is sort of splice it together and see that that point was in between the points of inflection and above it, so it was a relative maximum. Okay? So all we're doing today is kind of putting together everything from the last week. First derivative test to find extremes. Second derivative test to find points of inflection. Like I said at the beginning though, ignore the part of the directions today where it tells you to use the graphing utility. All you're doing is first and second derivative test, and then yes, you can kind of freehand sketch your graph, but the back of the book is also going to show you what the actual graph looks like. They're going to show you what a graphing calculator or a graphing utility would kick out if you were to do it. But for us, we're doing the actual work manually, first and second derivative test. Okay? All right, guys, shoot me your questions as they come up today. If there's a bunch of them, I'll put them together as a video. If there's only a couple individual ones, maybe I'll just reply individually by email, but we'll see how things go. All right, have a great Tuesday, guys.